Welcome to the Problem-Solving Pathway, a series of books that uses problems and games to teach basic problem-solving skills. The Problem-Solving Pathway is a framework of what to do, that is the stages to follow, to solve any problem. And how to do it, that is the tools or skills to use, and the steps to follow. Here is the definition of the problem statement. Turn this triangular shape upside down by moving exactly 3 coins, no more, no less. Now for the rules. Rules are generic, they apply to an entire family of similar problems. Firstly, do not get distracted by the name coin 0, it is just a name. All coins in this puzzle have the same size, shape, and weight. They look and feel identical. In other words, you cannot distinguish between coins. Move coins to a different location, but do not remove or discard the moved coins. Every coin that is present in the problem figure must be part of and belong to the final figure. No coin can be separate or orphaned from the final figure. In other words, all coins must touch each other, just like it shows in the figure. And we will learn how to ensure this final figure is a solution figure. When you experiment with intermediate stage figures, remember to compare them to the problem figure and not to other figures or previous solution figures. We begin our problem-solving quest by analysis. First, let us analyze the problem statement. The problem statement does not mention or state certain facts that are relevant to get a solution. But these relevant facts are implied or can be inferred. For example, just looking at the figure tells us that the triangle is made up of 10 coins. Another inferred or implied relevant fact is that the triangle points in the northern direction, or upward. Constraints are conditions a problem demands and forbids of each valid solution, in other words, what is legal and illegal in this problem. A quick distinction between constraints and rules. Rules apply to a family of similar problems. Constraints are specific to one problem. This problem has only one constraint: move exactly 3 coins. You cannot move less or more than 3 coins. You cannot walk around to the other side of the table, look at the triangle from the other direction and claim it is now upside down. That would be a constraint violation, since 0 coins would have moved. The goal is to turn the triangle around by obeying all the rules and constraints. Since the problem triangle points north, this implies that the solution triangle must point south. Do not remove coins or orphan them. The amount of coins in the problem and solution figures must remain exactly the same. As we have seen, this is an important rule. A very easy to understand but important tool is problem simplification. If you are given a problem and do not know what to do next, try to solve a similar but simpler version of this problem. Since the simple problem is similar to the more complex one you are trying to solve, both problems are said to belong to the same family of problems. So the same set of rules and a similar set of constraints will apply to both problems. Once you understand what makes this simple problem tick, you can tackle the more complex, actual problem. The simplest version of this triangular problem will have 2 rows of 3 coins. Row 1 has coin 0, row 2 has coins 1 and 2. Here, the constraint is to move just 1 coin to turn the triangle upside down. Which 1 coin do you think must move to give a solution? This solution is very simple and very obvious. Move any coin so that it touches the other 2 coins. Now remember to compare the solution figures shown next to the original problem figure. The first solution moves coin 0 to a new row below coins 1 and 2. Problem row 1, which was above row 2, disappears. Problem row 2 is now solution row 2, and contains coins 1 and 2. New row 1, that never existed in the problem, appears below row 2 and has coin 0 in the solution. For solution 2, row 1 has coin 1, row 2 has coins 2 and 0. For solution 3, row 1 has coin 2, row 2 has coins 0 and 1. Here is another evolved version of the problem. A 3-row triangle made up of 6 coins. This problem is slightly more complex than our earlier example problem, but still not our real 4-row triangle made from 10 coins problem. This problem's constraint is to move 2 coins and turn the triangle upside down. Can you guess which 2 coins must move? A word of advice for solving any problem: do not guess at random. If analysis fails to point you to a solution path, make an educated guess that supposes as little as possible and gives more importance to what you really know. And what you know that will help solve this problem are called relevant facts. Do you need a hint? The complete triangle is a composite structure. It is made up of simpler structures called primitive structures. Primitive structures are smaller, and fit within the larger composite structure. Break the composite triangle structure into smaller primitive structures. Can you see smaller triangles within the larger triangle? If so, how many? Can you find other regular shapes within the large triangle? Define the coins with respect to these structures. Look for symmetry. To help you decide which coins to move, pause this video and try to find the solution on your own. When you are convinced you know the solution path, hit the play button. You can view the problem figure from 3 different directions. We hinted that there were other directions when we explained the constraint of moving 3 coins. Walking around to the other side of the table shows the triangle from another direction. The first direction is our problem figure, pointing north. Its apex or top is coin 0, the middle row contains coins 1 and 2. The triangle base contains coins 3, 4, and 5. The second direction points to the southwest. Here apex is coin 3, the middle row contains coins 1 and 4. The triangle base contains coins 0, 2, and 5. The third direction points to the southeast. Apex is coin 5, middle row has coins 2 and 4, triangle base has coins 0, 1, and 3. Note that all these directions are relative. For this equilateral triangle, each apex points in one of 3 directions: north, southeast, southwest for the upright triangle, south, northeast, northwest for the 180-degree rotated or downward pointing triangle. Depending on your perspective, the same triangle will point in all 3 directions simultaneously, without a single coin having moved. Which primitive shapes did you find within the composite problem figure? The large triangle contains smaller, or primitive, triangles made up of 3 coins each: 0, 1, 2 and 1, 3, 4 and 2, 4, 5. All these 3 triangles point north. And most important, did you find the south-pointing triangle 1, 2, 4? The other primitive shapes found within this composite 6-coin triangle are 3 diamond shapes, with 2 apexes per diamond, depending on how you look at it. The first diamond has coins 0142 or coins 4102. They are the same coins, but the diamond direction is reversed or upside down. Similarly, the other 2 diamonds are 3421 or 2431, and 5214 or 1452. While fitting a diamond into the larger 6-coin triangle, we see that one diamond apex coincides with one triangle apex. For example, diamond 0142 has apex 0 coinciding with the 6-coin triangle apex 0. 2 coins on either side of the other diamond apex form the second and third apexes of the 6-coin triangle. Here, the other diamond apex is 4. Its adjacent coins that protrude from and do not belong to the diamond are coins 3 and 5. and these are the other two apexes of the 6-coin triangle. Move the 2 coins that are adjacent to the second diamond apex, so that they are adjacent to the first diamond apex. The triangle has turned upside down by moving 2 coins. This is a solution. And in case you were wondering, using the other 2 diamonds will also turn this triangle upside down. Figures for solution 2 and solution 3 are coming up next. Always, one original problem apex disappears, and a new solution apex is created. And if you cannot understand the solution figure, or if you think it has not turned upside down, remember to compare each solution figure to the original problem figure. The second diamond 1 2 4 3 has apexes 2 and 3. Diamond apex 2 is between triangle apexes 0 and 5. Move coins 0 and 5 to the other diamond apex 3. The problem triangle apex 3 was pointing southwest. The solution triangle apex 2 now points northeast. In the solution 2 figure, problem apexes 0 and 5 are relocated. Coin 3 was an apex in the problem, but is moved within the triangle in the solution. Coin 2 was within the problem triangle. It has become an apex in the solution triangle. The third diamond is 1 2 5 4, with apexes 1 and 5. Move triangle apexes 0 and 3, which are adjacent to diamond apex 1, to the other diamond apex 5. This will change the triangle in a third direction, and is the third solution. In all 3 solution figures, coins 1, 2, and 4 never move. Only 2 triangle apexes move per time. And finally, we come to our original problem. Turn this triangle upside down by moving exactly 3 coins. Moving, or adding, 3 coins to row 1 can turn it into a 4-coin row. But this uses up all the allowed 3 coins. Now assume row 2 coins 1 and 2 are not part of the 3 coins added to coin 0, to make it the current 4-coin row. 1 more coin must be added to coins 1 and 2 since they are below the current 4-coin row. The constraint is violated, the goal is not achieved, this path leads to failure. Should you move coin 9 adjacent to coin 3, which means new row 4 contains coins 9 3 4 5, and new row 3 contains coins 6 7 8. If you do, you must now move coins 0 1 2, to turn this triangle around. Coins 9 0 1 2 have moved, and that is a total of 4 coins. The constraint is violated, so this is not a solution. A 7-coin circular structure is formed with coins 1 2 5 8 7 3 4. Coin 4 is in the center of this circular structure. Row 2 contains coins 1 2, row 3 contains coins 3 4 5, row 4 contains coins 7 8. There are 3 coins adjacent to this circular structure, coins 0, 6, and 9. These 3 coins are the apexes of the 10-coin triangle. For all solutions, all 7 coins in the circular structure never move. And all 3 apexes of the 10-coin triangle move. Move apex coins 6 and 9 to row 2. You now have 3 rows in place, containing 4, 3, and 2 coins respectively. Only coin 0 is out of place. Problem topmost row 1 with coin 0 becomes solution bottommost row 1. This is a new row with the same coin 0. Problem row 2 with coins 1 and 2 now becomes solution row 4 with coins 6, 1, 2, and 9. Row 3 remains untouched between the problem and solution figures. Row 3 coins 3, 4, and 5 never move. Problem row 4 with coins 6, 7, 8, and 9 becomes solution row 2 with coins 7 and 8. The problem figure base contains coins 6, 7, 8, and 9, its apex coin 0 points north. The solution figure base contains coins 6, 1, 2 and 9, its apex coin 0 points south. Solutions 2 and 3 are self-explanatory. Remember that the same 3 coins are moving, coins 0, 6, and 9. This might get confusing. Just trace the source from where each coin moves, and destination of where it moves to. For solution 2, move coins 0 and 9. They were adjacent to coins 2 and 5 in the problem. They are now adjacent to coins 3 and 7 in the solution. Finally, move coin 6. For solution 3, move coins 0 and 6. They were adjacent to coins 1 and 3 in the problem. They are now adjacent to coins 5 and 8 in the solution. Finally, move coin 9. When you know where to move the same 3 coins to, you can interchange the final positions you place the 3 coins in, and get different solutions. In solution 3, put coin 6 where coin 0 is, put coin 0 where coin 9 is, put coin 9 where coin 6 is. Effectively move the 3 coin positions anti-clockwise. And this gives solution 2. If this brief introduction to problem solving has interested you, direct your steps to the problem-solving pathway. Here you will find more free resources that make learning problem-solving fun. Critique and queries can be addressed to info@problemsolvingpathway.com.